So here's our problem. A 4-kilogram model rocket is launched shooting 50 grams of burned fuel from its exhaust at a speed of 625 meters per second. What is the velocity of the rocket after the fuel has burned? So we're going to, and it says to ignore air resistance and gravity and all that. So if you do that, you're saying that the rocket and its fuel are a closed system. There are no external forces on the system, so therefore you can say that momentum is conserved. So here's what's given. We've got a rocket. Now let's do the before. And I'll just draw, some model rocket like this and put some fins on it or something. And it's got a certain mass. Now, what is its mass, by the way? The mass is before is, well, actually, let's just say this. The mass of the rocket is 4.00 kilograms. And let's say it's the mass of the rocket without the fuel in it. The mass of the fuel is 50 grams, but let's change that to kilograms. 0.050 kilograms is the mass of the fuel. And then we know that the initial velocity for both of them is 0. The rocket is at rest. Then it fires. And so here's our rocket after the fuel has been expended. And it's got some final velocity of the rocket. And then here's all the fuel that's come out of it. And it's all spread out, but it still has a mass. The mass of the fuel, 0.05 kilograms, and it has a velocity to the left of 625 meters per second. And so what we're trying to find is that final velocity of the rocket. So when the engine explodes, when there's an explosion, and you have this closed system, the momentum of the system is conserved. So start off with the initial momentum of the system is equal to the final momentum of the system. The initial momentum of the system is 0 because it's not moving. The final momentum of the system is the mass of the rocket times the final velocity of the rocket plus the mass of the fuel times the final velocity of the fuel. I guess I'll make capital F fuel here. All right. And so now I know the mass of the rocket, the mass of the fuel, the final velocity of the fuel. All I got to do is solve for that. And that's where you get that equation in the back of the book. When you look in the back of the book and they say, oh, the velocity of the final velocity of the rocket is equal to, well, you bring the mass of the fuel times the final velocity of the fuel. Well, you subtract it, so you're going to have a negative over here. What did I do? I made it an E. Sorry about that. Divided by the mass of the rocket. Now this negative is going to cancel out here. We'll see in a minute. So now I can plug in my values. I got negative. What's the mass of the mass of the fuel? Is 0.050 kilograms times the final velocity of the fuel. Now, I didn't really put it on here, but it's going to the left. And I'm going to say that to the left is negative. So it's negative 625 meters per second. And then we're going to divide that by the mass of the rocket, which is 4.00 kilograms. And so what's the final velocity of the rocket? The negative cancels the negative, and you plug all that in, and what is it? Please help me out. 7.81 meters per second. And it's positive, which means it's to the right. Okay. Any questions on that? So again, it's conservation of momentum.